Welcome to a new video. In this video we will discuss the inverse matrix. We will discuss how we can determine the inverse of a matrix using several methods for 2x2 and 3x3 matrices. We will see that, of course, using some examples and calculations and verifying these in MATLAB command window. First we start with the introduction to give you the definition. Now if you have a matrix, let's say called A, we use most of the time capital letters for matrices, and it is a square matrix, so n by n, meaning n rows and n columns. An inverse of this matrix A is denoted by this a to the power minus 1 is also n by n, again a square matrix, will have a property that the A times the of its inverse will be the identity matrix, or the inverse times the A is also the identity matrix. So these two properties must have this inverse matrix. The matrix I is mentioned is called the identity matrix and also has the same dimension as the matrix given here, which is the matrix A. Now there are some rules, there are actually many rules, but these are the most important rules to mention here. As said before, so A times its inverse is also its inverse times A and will be then result in the identity matrix. If this is true, then we have also the inverse of that matrix. We can also do the inverse of the inverse will always result in the original matrix A, and it must be a square matrix, so you cannot use it for, let's say, 3x4 matrices or other types of matrices, so it must be a square matrix. And we also know that the determinant of that matrix is not 0. This is a very important condition in order to check that the solution of your system is unique or not unique. Okay, let's start with a 2x2 matrix in general form. Let's say that we have the entries A, B, C, D, so 4 entries. And how do we now determine the inverse of this matrix? Now, this is only valid, as said before about a determinant, if the AD minus BC is not 0. So then we say that the matrix A is invertible. Why is this the case? Because if you look at the formula for the inverse of a matrix, this is only valid for 2x2 matrix. You see here 1 over the determinant, and if the determinant is 0, then we have a problem, because then we get here 1 over 0, which is then not defined. In addition, you see here the matrix here is written in a different form. So you see actually the A and D are swapped. So you see here the D and the A, and the B and the C has a negative sign here. So they have an opposite sign. So that means the determinant, which is defined as from here, the cross multiplication here minus the cross multiplication there. So AD minus BC, which is actually shown here, must be not equal to 0, otherwise you can say this is not invertible. So if that is the case, then A is not invertible, so there will be no solutions, no unique solutions. Let's give an example. Let's use numbers. So let's say that the A is equal to 2, 6, 1, 4, so that means A, small letter A, B, C, and D are given now here. Let's see if this is invertible. Now, first we calculate the determinant, otherwise there is no point using this formula. So the determinant of A is 2 times 4, this is here, and a minus 6 times 1, that's shown here, so we get 8 minus 6, which should be then 2. So this is not 0, so this is invertible. That means also the following. Matrix A has independent rows, that means independent rows and independent columns. What does mean independent? You cannot make this matrix from this, this row from this row, because if I can make this row from this row, I need to multiply that by a scalar, which is not possible. It's also not possible for the columns. Let's see another example, so that will be given more easily what's happening. Let's also calculate first the inverse of this matrix. So A inverse is then 1 over 2, because that was the determinant from this formula, and then we swap this, so this is 4, this is 2, and we give here an opposite sign, so minus 6 and minus 1. So we can also use this half inside this matrix, so you get a 2 here, so you divide everything by 2, and this is the result. Now let's see that also for another example. Now we have this matrix B, which is now given by 2, 6, 1, 3. So we only change this 4 into 3. What happens now? Let's see if we can also find the inverse of this matrix. We first determine the determinant. So determinant of this b is 2 times 3, which is shown here, minus 6 times 1. That will be then 6 minus 6, so that is 0, exactly. So that means b is not invertible. That means makes b has dependent rows and columns. Can we see that already from here? Now, for a 2 by 2 matrix, it's pretty easy to see that. For a 3 by 3 or 4 by 4, it can be difficult. You see, for example, this 2, 1 for this column, first column, and we have here 6 and 3, but this is 2 times this one, so I can make this from here, I mean 3 times, so this column can be produced by multiplying this column by 3. Or you can say I can make this row by multiplying this row by 2. So they are dependent, so that means I cannot make here a inverse. So the solutions, if I want to find the solutions for this matrix, for any other vector, there will be no unique solution, so there will be infinite solutions. Okay, so again, the definition: if matrix A is invertible, and it will be of course a square matrix, then the equation we have here, AX is equal to B, for this solution X, and we'll have a unique solution if the A has an inverse, and that can be then written like X is equal to inverse of this matrix times the vector B. Okay, let's see that in more detail using an example for this equation. Now, given is the matrix equation we have here, and we have the matrix again, the same matrix A, but now we have a B, which is this vector, which is 5, 4, and 5. So how can we now calculate and solve for X? Now, we need the inverse. We already have that inverse, so we can directly go to the formula, and we can substitute here the inverse and the vector B in order to calculate the vector X. So this is the formula for the inverse, again as shown here, but then in more detail for the determinant. We have already done this, so this will be then the result. Now I need to now multiply this by this vector. So then we have the vector X will be the inverse of this matrix times the vector B. So how does it work? Now we have here 2 and minus 3. That will be multiplied by this column, so this is the vector, so that will actually go like so. So this row of this matrix will be then multiplied by this vector. That goes in this form: 2 times 4 plus minus 3 times 5. That's actually shown here. And the next one is this row, so you do 1 by 1, and again this column, so minus 0.5 times 4 plus 1 times 5. So you see that here. Now this will be 8 minus 15, and this is minus 2 plus 5, so that will add up to minus 7 and 3. So we have here now the vector X, the entries for our solution. Okay, great. Now let's also do that for 3 by 3 matrix. Now for a 3 by 3 matrix, there is unfortunately not a simple formula as we have it for a 2 by 2 matrix. So you cannot use this, let's say, pretty straightforward and easy formula. We can use two methods for determining the inverse of a matrix. Now, the first method is called the Gauss-Jordan method for the inverse matrix. The second one is the cofactor method. And we will discuss both of them briefly in the definitions and also give an example. Let's start first with the Gauss-Jordan method for computing the inverse matrix. Now, the procedure goes like so. We have a matrix A. We add to that identity matrix with the same dimension, and then we proceed with Gaussian elimination, Gauss-Jordan elimination. In order to get here an identity matrix, then you get here at the right side your inverse matrix. So consider in general this matrix A, B, C, D, E, F, G, H, I, so in 9 elements. We add here, so we add to the given matrix an identity matrix, so it will be then augmented. So you get actually the same dimension, but then 3 by 3, so 1, 1, 1. So at the diagonal, the rest of the parameters or the entries are 0. So you augment your matrix with an identity matrix having the same dimension as matrix A. So if you have a 2 by 2, you will have a 2 by 2 identity matrix here. If you have a 5 by 5, you will have a 5 by 5 identity matrix here. Then we apply Gauss-Jordan elimination to reduce the augmented matrix from this form into this form. So the goal is to create here at the left side an identity matrix, exactly identity, and then you can look at the right side and you can find your inverse matrix. Let's see that in action, but we start first with a 2 by 2 matrix to illustrate the concept in an easy way. So again, we use this procedure. So we first augment this given matrix. We already did that using the formula. That's actually a 2 by 2 matrix, so there is no need for Gauss-Jordan method. But we illustrate this also here to see that clearly for this method. So we augment this as shown here. So we augment it with a identity matrix. Now we need to make the row reduction, elimination, in order to get here the identity matrix, and then we look right side and we recognize our inverse matrix. So I start first with multiplying the second row by 2. Why? Because I want to make this 0. So that goes first. So they get now here, this row 1 is the same. This is doubled. 2, 8, 0, 2. You see that here. That's the only change. That means just 2 times the row 2. Next step is I will do the row 2 minus row 1. This is the basic row reduction or elimination in Gaussian elimination method or Gauss-Jordan elimination method. We have also discussed it in the previous videos. Now we will do that. So we go one by one. So element wise, you do 2 minus 2, 8 minus 6, etc. So we see here that the result 2 minus 2 is 0. That's also what we did here in order to do that. 8 minus 6 is 2. 0 minus 1 is minus 1, and 2 minus 0 is 2. Okay, this is still of course not what we want, but we're getting closer because we already have this 0 here, because we want this identity matrix shifted to the left side. So there's already an entry which is 0. So I need to also make this 1, make this 1, make this 0. So now next step is make this 0. That can be done by multiplying the second row here by 3, so we get here a 6. So that's the next step. So first row we just copy, and second row we do that multiplication by 3. So 0, 6, minus 3, and here also 6. And then the next step, I will do that here. That will be then row 1 minus row 2. So then row 1 will be changing and row 2 will be not changing. So you just copy row 2. This is now 2 minus 0 here. 6 minus 6 will be 0. 1 minus minus 3 will be 4. And 0 minus 6 will be minus 6. So now you see already that we have another 0, which is then we're getting closer to the identity matrix. I now need to make this 1 and this also 1. So that can be done pretty easily by dividing this by 2 and this is by 6. And this is what we now do here. So row 1 by 2 and row 2 by 6. Now you get here the following result. This is then 1, 0. This will be then, because you divide by 2, will be a 2. This will be a minus 3. You divide this by 6, so there will be 0 still. This is a 1. This is a minus 0.5, and this is 1. Now you see here this identity matrix as we wanted, and here if you look to the right side after this vertical line, that will be your inverse. And this inverse we also had from the formula we have seen before. So we can say that our inverse matrix is indeed as we have calculated, and that's also determined from this Gauss-Jordan method. Okay, now let's also look at it in the MATLAB. So if this is really correct. Now this is the MATLAB command to create this matrix 2614. We use this inf and parentheses a to calculate the inverse of this matrix, and now we have here the result. You see the 2, minus 3, minus 0.5, and 1. So this is indeed as calculated. Now let's see that also for a 3 by 3 matrix, because that is more interesting. Now we have here now 3 by 3 matrix, or 9 elements. How do we work it out? Again, we augment this matrix. Now in this case we need to use an identity matrix which is 3 by 3. And we proceed again in order to make this 0, this 0, this 0, that's really the order, and then this 0, and that 0. And then we need to do the final step in order to make this all ones. So we do more steps here because we have a 3 by 3 matrix. We start first with making this 2 times and making this also 2 times, so we have all 2's here. So what we have is double the first row and double the third row. So the second row is just a copy. You just take it over, double this, we get here 1 times 2, so 2, 4, 6, 2, 0, 0. You double this, so it will be then 2, 0, 16, 0, 0, 2. That's all shown here, so everything must be doubled. So we need to check this carefully. Then we can do row 3 minus row 1 and row 2 minus row 1. Why? Then we have this 0, that is 0. So these are the two operations I do one by one. That means row 1 will stay the same. So I take that first, copy that, and I will do this first. So 2 minus 2 is 0, 5 minus 4 is 1, that's shown here, 3 minus 6, that's minus 3, 0 minus 2, that was minus 2, 1 minus 0, 1, 0 minus 0 is 0. Next one, 2 minus 2 is 0, 0 minus 4 will be minus 4, 16 minus 6 will be 10, 0 minus 2 will be minus 2, and 0 minus 0 is 0, and the final one is 2 minus 2 is 2. Now, next step is I need to also get rid of this one, so I can say let's make the row 2 4 times. That's what we can do, but we can also say in a different way. You can say let's divide this first row by 2. That is a different way to do that, and also you can also divide now the third row by 2. Let's do that first. So there are different ways to go, but I will also show you that. So what we have is then everything is then here divided by 2, and here also divided by 2, and this is unchanged. Now what do we do next? Now we can now look at this, and this is the procedure I want to make. Now we can say I want to also double this second row. The second row. Why do I do that? If I do that, I can also get here a 2. So that is then everything is now in 2 2's here, and I can now make this operation easily. So only the second row is changing. Now the first and the third row can be just copied. So double this, double that, double that. So every entry here in the second row, and you get these values. Next one. Now we need to make this 0. That can be done by using the R3 plus R2. Because then we have a 0 here. This is 0 plus 0, minus 2 plus 0, and etc. Then you get the results here. You see that here, minus 1 plus minus 4, 0 plus 2, 1 plus 0. So you see here the results. Now we're getting already closer because this is 0, 0, 0. Now we need to make these 0, and then final one, we need to make this all ones in the diagonal. Okay, next steps. Oh, what do we do next? Now I need to make this 0, so let's make this 6. That means let's double this, because I need to make the 3 into a 6. That means, and I also need to make this something which is later also with a 6. So let's also make this 6 times. Okay, now we have this. You see here now the row 1 has changed because we doubled everything, and row 3 has changed. We also multiply by 6. So you see all the entries here are times 6. The next step is then row 1 plus row 3. Why not row 2, you might say? It is easier to do that with the row 3 because we get here more zeros. It doesn't matter, you can also use this, but it is handier to use a row which has more zeros. Okay, now we will do that. So that means the following. And we can also do row 2 minus the row 3. That is another step, so we get also a 0 here. So we do 2 steps at once here. That means row 3 will be the same, so it doesn't change. This will be then, by this operation, change this one. So you can also see that by looking at this one. So 2 plus minus 30 is minus 28. 0 plus 12 is 12. 0 plus 6 is 6. So in the other case, you also do the similar case, but then use row 2 minus row 3. Okay. What do we do next? Now we have already here 0, 0. We're getting closer and closer to the situation we want here, which is an identity matrix 3 by 3. I want also get rid of this one. So I can say, let's divide this by 2, or let's double this in order to get the same value here. So I divided now this by 2, so I want to get smaller values. So I have here 1, 2, 0, minus 14, 6, and 3. The rest is the exact same. Now the next step is, as mentioned here, we need to now do the row 1 minus row 2, because I want to have a 0 here. That's now happening here. You see that? And that is not changing. That is not changing. So row 2 and row 3 are just exact same. So we just copy them. Only change is the row 3, or I mean row 1. What happens next? Now we are now very close. We only need to make this one. It's already the one, but we need to make this one. And we also need to make that one. So that means we need to divide the second row by 2 and the third row by -6. That's shown here. So we just copy again the first row. That's good. Second row we need to divide by 2. So it will be then 13 minus 5 minus 3. We divide this by -6. So it will be then 1, 5, -2 and -1. Now you can see here the identity matrix in the 3 by 3 dimensions. So, and we have here the right side, its inverse. So we have here the A inverse is the matrix. Here we see here the entries. You can check this by multiplying this matrix with that matrix, and that should result in the identity matrix. That is the check you can do. Okay, now let's check that also in MATLAB. Now this is again the MATLAB command we did also for a 2 by 2 matrix, but in a similar case. Now for a 3 by 3, you see here 1, 2, 3, first row, second row, 2, 5, 3, and 1, 0, 8. This is also shown here. Now we also calculate the inverse of that matrix by this command, and this is the result. You see here -40, 16, 9. That's the first row. 13 minus 5 minus 3, 5 minus 2 minus 1, and that means next to each other. You can see that clearly. That is indeed correct. Okay, now we also discussed the second method, which is the cofactor method for computing the inverse. Now this method requires more calculations, but it is easier to follow in some cases because the row reduction can be sometimes difficult to follow because you have minus signs, etc. It depends which one you prefer. This works also fine for 3 by 3 matrices. Now how does it work? Now we have this formula which says again the inverse, but then you need to know the determinant, but it is now multiplied by this adjoint of this matrix A. So in general, consider this matrix 3 by 3 matrix. That adjoint of this matrix is given by this expression. We have here now 9 elements, 9 cofactors actually, which is also to the power t, which this t stands for the transpose of this matrix. So this is adjoint of this matrix, which is called the C matrix, which is the cofactor matrix, and this T is called the transpose. We will discuss this shortly what the transpose means. So if this matrix C is then given by these 9 elements, which are on their own again matrices where we calculate the determinants, this then will be by the transpose operation converted in this one. So you make actually from these rows, you make a column. That means transposing. The second row goes to a second column. Third row goes to a third column. That is how this transposing works. And then cofactor matrix is then given by this operation. You see here the plus, minus, plus, minus, plus, minus, plus, minus, plus. So you actually see the switch in the minus and the plus signs. And you see also here the entries. So how do we determine that? That goes like so. You look at the first entry, so top left, and then you cross over the row and the column, and what's left is E, F, H, I. That is what we see here. Now we go to the second entry, B. You cross over this row and the column where it is. That means this T is actually gone. D, G, F, I. You see that also here. But it should be, of course, multiplied by -1. Then for C, we cross over this row, because that's in that row, and also in this column. What's left is this. So these 4, so D, E, G, H. D, E, G, H. Now, in the similar form, you do that for the other 6. Then you get here 9 determinants. So it can be then, it takes some time to calculate this, but it is, if you do that carefully, it's not that difficult. Okay, so then we have here the vertical lines. So if I take this for example, or this as an example, A, B, D, E, the vertical line of this matrix means the determinant of this matrix A, B, D, E. And that is then of course calculated as we have done it before, A times E minus B times D. But how do we calculate what is actually C11? C11 is this entry. Just look at it. So this is actually shown here. And C12 is this entry with the minus sign. And C13 is this entry with the plus sign. And C21 is this entry. And C22 is this entry, etc. So you can go on and you have these 9 values. So you actually need to calculate these 9 determinants and put it here in this matrix. Make a transposition of that one. And also calculate the determinant of that complete matrix. And then you have your inverse. Let's see that in action. Again, the same matrix as we have done it for the Gauss-Jordan elimination method for computing the inverse and using this formula. Now, we first calculate the determinant of A. Now, there are many methods to calculate the determinant, and there is a way to also do it in a shorter way. You choose a row or a column where there is a 0 or many zeros. In this case, there is a row here, which is a third row, which has a 0, or the second column. I go for the third row, and there is also here an order, very important, because you start here, which is plus, minus, plus, minus, plus, minus, plus, minus, plus. So you actually need to change sign, depends on where you are. So in this case, if I start here, and I will use this row, that means 1 times this part of the matrix, which I calculate the determinant, which is then 2, 3, 5, 3. That's shown here. It is a plus, and then minus 0, so that is the advantage, because 0 times something, it doesn't matter, so it goes. But I will show that clearly what it is, because it is now 0 here. I cross over this one and that one, because that is the column and the row, and there's 1, 2, 3, 3. But that it doesn't matter which value this is, it's still 0 times this, it will be 0. And then the final one is a plus, so 8, and then I will cross over this one, cross over that one, it will be then 1, 2, 2, 5. That's shown here. Now I need to calculate that using the formulas for determinant. So this is then 2 times 3, 6, minus 3 times 5, it will be 15. So 6 minus 15 times 1, minus 0, and then plus 8 times 5, 1 times 5, minus 2 times 2, so minus 4. Now this is then minus 9, and this is 8 times 1, so 8, so minus 9 plus 8 will be minus 1. That is indeed not 0. So I can say, thus the A is invertible. I can say this is not 0. This is the first check you need to make, because if this is 0, you can say that this is then undefined, so you can just say there is no inverse of this matrix. Now, next step is the calculation of the components of our cofactor matrix C. Now we have here 9 elements. So we have C11, C12, etc. C11, how do we calculate that? As we have discussed this in the previous discussion of the definition, you look at the left top, that is the C11 location. You cross over this row, you cross over this column, and you look at 5308. That is this one. Now we need to use a definition of the determinant for a 2 by 2 matrix, which is then 5 times 8 minus 3 times 0, which is 40, minus 0 is 40. Now C12, which is here, is there, but it should be also with a minus sign in front of it. And we cross over now here this row and this column, because that's where this element is, the location of this C12. And now we see here 2, 3, 1, 8. Here, you see that here, 2, 3, 1, 8. Now we need to again use a formula for the determinant, 2 times 8 minus 3 times 1. That's shown here in the parentheses, because we have a minus sign here, so you get here 13. With a minus sign, you get a minus 13. Now, C13, which is this location, you cross over this column, this row, 2510 is left. So 2 times 0 minus 5 times 1, which is then 0 minus 5 will be minus 5. In a similar case, you do that for the C21, C22, etc. So again, plus, minus, that order needs to be used. And we have now our 9 elements here. Let's see that here, 40, minus 30, minus 5, that's shown here, minus 16, 5, and 2, that's shown here, minus 9, 3, and 1, that's all shown here. Now we have our cofactor matrix. Now the next step is create this adjoint matrix that is then given by adjoint of that A is this matrix, cofactor matrix, with a transpose of that one. So you need to transpose this matrix. So how to do that? Now you make this row, you make a column. Here we go. So you get here 40 minus 13 minus 5, you put it now here vertically. Now this horizontal, minus 16, 5, 2, you put it like so. In the second column, now the third row will be a third column, minus 9, 3, 1. That's shown here. So then we have that A inverse is 1 over minus 1, because that was our inverse, the determinant of this A. And then here the adjoint of that A, which is here. And then we can now use this minus 1 also inside. Sometimes it is not a nice number, like 1 over 7, then you can better keep it outside. But in this case, we can put it inside. So you get here minus 40, 16. So everything is now in the reverse sign. And you get here your inverse matrix. And this was the exact same matrix as we have calculated using the Gauss-Jordan method. And this was also found from the MATLAB command window. So again, repeating here, we define this, we calculate that. We will see that also here, and this is the result. You see actually also the same result is produced here. Alright, this was our example considering the inverse matrix of 2 by 2 and 3 by 3 matrices, but this method can be also used for 4 by 4 and other larger square matrices. We have discussed the Gauss-Jordan elimination for the inverse matrix and also the cofactor method for computing this inverse matrix. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. See you next time in another video.